Alrighty, welcome back to operating systems. So today we are going to talk about, oops, I should unmute that, there we go. All right, so today we are going to talk about threads implementation and how you might implement threads if you were to cough, cough, wink, wink, implement it yourself coming tomorrow. So let's get into this because this will be useful. So there are a few multi-threading models, so you might ask yourselves, well, where do I actually implement the threads? So there is actually two options. Well, there's actually three, but the two main ones is I could implement the threads as kernel threads or user threads. And what's the difference between them? Well, kernel threads, the kernel knows about, so the kernel knows they are separate execution streams, while if they are user threads, that just means you are creating your own threads, you are faking it. As far as the kernel is concerned, it's only executing a single thread, and then you are concurrently switching between that on top of that thread. So the user threads are completely in user space, which means that they're just part of your code. The kernel doesn't treat your process any differently. So if you do user threads, your process only has that one main thread that the kernel creates. And then as far as the kernel is concerned, there is no notion of any other threads existing in your process. So you just create them, and that is what you will be doing in Lab 3. The alternative is to have kernel threads that are implemented in kernel space. So the kernel actually knows about the threads, so you would have to do a system call to create them. And then after that, the kernel manages all the resources for you, and it can actually schedule threads separately because it knows about threads. So it could run two threads in parallel because the kernel knows about them. While if you just have user threads, you can't do anything in parallel because your process will only have a single main thread, and that is all the kernel is concerned about. It will only execute one thing at a time. So if you need thread support, it requires something like a thread table, which is also analogous to a process control block, similar to the process table. So it could be in kernel space or user space, depending on if you're implementing kernel threads or user threads. So if you're doing user threads, which you will be doing, there is also a need to have your own scheduling system on top of it. For our purposes in Lab, 4, you will just be doing first in, first out, first come, first serve, so the easiest scheduling we could do. But you could implement your own, not for the test case, but if you wanted to, you could implement your own scheduling and take your user threads way further. But in both models, a process contain multiple threads. It's just whether or not the kernel is aware of the multiple threads or not. So we could avoid system calls and let a thread block. So for user level threads with no kernel support, they're going to be really fast to create and really quick to destroy because there's no system call associated with them, no context switches at the kernel level. You have to do all your context switches yourself while your program is running. But the big drawback for having user threads is, well, because the kernel only knows about one thread running in your process, if one of your thread blocks by doing a read or a write or any other system call that blocks or doing a sleep, then your process, no other thread will execute because as far as the kernel is concerned, that process is now asleep, can't execute anything else. If you have kernel level threads, they're going to be slower to create because they necessitate a system call. But the nice thing about kernel level threads is, well, the kernel knows about them. So if you have like 8 threads in your process, if one of them does a sleep or blocks, well, that doesn't affect any other thread. The other 7 threads can go ahead and still execute. The kernel could even run them in parallel if you had enough resources. So all the threading libraries you run have some aspect that runs in user mode. And then the thread library will be responsible for mapping those user threads to kernel threads in whatever fashion it wants. So pure user space threads, that's what's called many-to-one. So it's how many user threads map to one, or map to how many kernel threads. So in many-to-one, that means all your user threads map to a single kernel thread. So it's purely implemented in user space. Again, the kernel is not aware that your program, your process actually has multiple threads. It doesn't care. So if that process blocks, that process just can't be scheduled anymore. So the other scheme, if you want one thread to map to one kernel thread, that is called one-to-one. So each of the threads in the library actually maps to a kernel thread. The kernel handles everything. There's just the thread library is just responsible for doing some light accounting and figuring out, numbers to threads and things like that. So P threads are an example of one-to-one. So they are actually in kernel threads. So that's why if you have multiple threads, they will, if I have 8 threads and I have 8 cores on my CPU, well, it could schedule them all in parallel. They could all be running at the same time because they are kernel threads. There is another option, and that is many-to-many. So I can map a bunch of user threads in the library to one or more kernel thread. Generally, there's more user-level threads than there are kernel threads, and you cap this at the number of kernel threads that matches your hardware, because anything on top of that can't really run in parallel. So that is another option. So, like I said, many-to-one, pure user space implementation. The kernel is only aware of a single thread, and everything is on top of that. So this is what you will be doing in Lab 4. So it's going to be fast, going to be portable, doesn't depend on anything. It is just a library. But the drawbacks are if one thread blocks, all the other threads block, because all the operating system cares about is scheduling that one thread it knows about in the process. Also, like I said before, nothing can be done in parallel because at the end of the day, your kernel, is that like a gas leak? Okay, it stopped. We are saved. All right, woo. All right, so in this case, we can't execute any threads in parallel because, again, the kernel only knows about that single thread. So if one blocks, the whole process blocks. The other one, again, like I said, harping on this, one-to-one just uses a kernel thread implementation. So there's just a thin wrapper around some system calls to make it easier to use. And this is essentially what the pthread library does. So that allows you to exploit the full parallelism of your machine. The kernel can schedule each thread on a different core, run them all in parallel, which we learned what the difference between concurrency and parallelism is on the last one. So it could run them all in parallel, but it has to use this slower system call interface, and you lose some control. So if we are doing a pure user thread library, well, you actually have some say with the scheduling. But if you're doing the kernel version of it, you don't have that much control. You have as much control as with what we saw before with the process. So you might be able to adjust your priority a little bit, but ultimately you have no control over the schedule. So typically, this is the actual implementation that's used, and this is what we'll assume for Linux using pthreads. So many-to-many is a hybrid approach, and the idea is, while we have more user-level threads than kernel-level threads, so I will cap the number of expensive-to-make kernel-level threads to match the number I could actually run in parallel on my machine. And the idea behind that is you get the most out of your CPU and your system with the fewest number of system calls. However, this really leads to a complicated threading library. It tends to be popular for a while and then die out and then come back. So recently, it has come back if you're using Java. So Java virtual threads use this idea. Typically, it's really complicated to get right because any of these threads could also block. And if one of the threads blocks, whatever is mapped to that one kernel thread would also block. So sometimes you might not want that. You might get really weird performance, and you could block a lot of threads. One execution, you might get lucky. One you might not. So typically, it's really unpredictable and hard to get right, and people generally avoid it. Yeah?
Did you say that it's the minimum number of calls?
Yeah.
Why is that?
So the minimum number of system calls, so say I wanted to create like 1,000 threads. Well, if it was 1-to-1, I would have to do 1,000 system calls for each kernel thread. If I did many-to-many, I might just make 1,000 user threads, and then if I only have 8 cores on my machine, I will only make 8 kernel threads. And then I'll figure out a mapping from those thousands, split them up into like, what, 125 each? Something like that. But the drawback is, well, if one of those 125 block that's running on the kernel thread, the other 124 that are also mapped to that kernel thread will also block. So you might get, typically this comes and goes with the time. Apparently it's new again. So if you see Java virtual threads, their new feature, that's what this is. And I would avoid using it. So threads, we haven't even talked about how they would complicate the kernel. So for example, if I have multiple threads that are running and they're kernel threads, what should happen when I fork? So if there's 8 threads running and I fork, what happens? Do like the new process is an exact copy? Do they just, that new process also has 8 threads and it's just whatever state they were in when the copy was made? How would that get out of hand really, really quickly? Well, remember that I could essentially accelerate that fork bomb. So if I had like 1,000 threads and then I had each of them doing like a fork bomb thing, well, then I multiply it I multiply it even quicker than I did before. So the rule behind that is actually a fairly simple rule. So whenever you call fork in a process with multiple kernel threads, well, Linux is only going to copy the thread that initiated that fork call. So your new process will only have a single thread, and that single thread will be a copy of the thread that called fork. So if I have 8 threads and one of them calls fork, I would create a new process with only one thread, and it would be a copy of that thread that called fork. So my new process would continue on with only a single thread. And because of this, well, if it hits pthread exit and it's the only thread in the new process, it would just exit the process because it is the only thread available now. So it will go ahead and call pthread exit and all that as far as I can tell. There's also pthread at fork, which we will not cover in this course, because as you might imagine, if one thread is calling fork, you don't know what the other, say, 7 threads are doing. So you might want to make sure your program is in some type of consistent state so that that new process is consistent whenever it gets forked. So you're allowed to control what happens at a fork using pthread at fork to make the state consistent. And again, that will be too complicated, not covered in this course with how to do that and make things consistent, but you should know about its existence and that, yeah, it's probably a giant headache. Yeah?
Sorry, so what if you have 8 threads and you call the fork?
And what, sorry?
And you call the fork.
Yeah, so if I have 8 threads and then one of the threads calls fork, it will create a new process that is a copy of the old process, so like we had before, but the new process will only have a single thread in it, and it will be the same thread that called fork. If that kind of makes sense. If not, we'll have we'll come up with an example. So, also, we have to think, oh, if I have a process with 8 threads and a signal gets sent to the process, what should happen? So which thread should receive the signal? Should it be the main thread? Okay, well, if the main thread doesn't exist anymore, should it be all threads? Well, then each thread tries to do the same thing, so you might be doing the same thing 8 times. So the Linux solution to what happens when a signal gets sent to a process with multiple threads is to just send the signal to one of the threads. Which one of the threads? Yeah, it just picks it at random. So it will just randomly send the signal to any old thread. You don't get control it. And this makes concurrency hard because any thread can be interrupted at any given time due to signals, and this is another reason why people actually do not like signals. So that's fun. So another thing is, well, you might think that many-to-many is actually a good idea. So what you can do instead of implementing a whole threading library on top of it, you can use something called a thread pool. So, because remember, the goal of many-to-many is only to avoid the thread creation costs, avoid the system calls. So if I only have 8 cores on my machine, I can just create something called a thread pool of 8 kernel threads, and then you can just have a queue of tasks, and then each thread can just grab a task off the queue and just do the work as long as there are some tasks to do. So you can actually run up to 8 things, for example, in parallel, and with only creating 8 kernel threads. So as requests come in, you might wake up the thread, tell them they got some work to do, and then they can go back to sleep. And if there's no work to do, they don't have to run. So you might see this once you get into, like, if you start caring about performance on your machine, you can use something like thread pools. In fact, in Python, there's like, you can look up thread pools in Python, you can use thread pools in Python. So that is a good way to make your programs run in parallel. So like I said, lab 4, you're going to implement many-to-one, and this state diagram may help you because your threads are going to follow the same state. So the library you're going to create is called what, or wacky user threads. So I'm easily amused, so I just made a 3-letter acronym that, I don't know, amused me somewhat. So whenever you create a thread, you're going to create your own thread through a function called whatCreate. So that should create a new thread for you and put it in this waiting state or ready state. And since you are doing user threads, only one thread can be running at any given time. So eventually, whenever you do FIFO order, it will be running, and then we're going to do cooperative threads. So they can actually yield, which would mean that they can, go ahead and put themselves on the back of the queue and another thread can run. So you will have an explicit call to yield that will put the current thread back into the ready queue and essentially make sure that the next thread is going to run. So it just context switches to the next thread. And that will be done through a nice helper library that we will explore in the next lecture. So you don't have to do any of the hard context switching. Most of the heavy lifting is done for you. So while a thread is running, it may become terminated by calling exit. So that would make that thread terminated, and in which case, well, you would have to go through, you would not clean it up, you would set its status code and everything like that, and then start running the next thread. If there's another one to run, if there is not another thread to run, well, this should just exit the process like we saw before with pthreads. You will get into the situation where some threads can block. So you are going to implement join. So you are allowed to join another thread. So in that case, whatever thread calls join will block until the thread it is trying to join actually terminates. So that will block the thread, and then whenever it terminates, we'll have to go and take this blocked thread and then put it in the ready or waiting queue whenever the thread it's waiting for has terminated. So this is what you'll be juggling in lab 4. So this is like a vastly simplified version of the old lab that took like 80 hours. So this one should not take that long. If this one is like super daunting, please, I haven't seen any feedback for labs, or at least the last lab. So please use the feedback channel if you have any comments or anything like that. This lab, however, shouldn't be too bad. Yeah. Yeah, can we get another help video for that lab? And that's the next lecture. So next lecture, we will be doing a real video. So I'll show you how to do all the context switching and everything like that. I'll show you how to do a queue. So there'll be a queue you can use. You don't have to implement your own. And from last year, I updated the documentation, added some more help things. And there'll also be an incentive to start early because you get to write a test case and you have a week to do it. So you get to see how it works to encourage you to, actually try it. All right. So with this, your schedule, oh, yeah?
What do you mean we have a week to do it? Like it's due next week?
Yeah, so you can submit a test case and you'll have a week to do it. And it's like worth like 5% or something of the lab.
Okay.
So a very minimal mark. If you want, forget it. It's mostly so that you know what it is. So you get to write a test case that does whatever you want, and it runs against the solution, and you get to see the proper output of it. So if you are confused about anything, you can write a test case for it, and then I will run the solution on it and then tell you what the output was. So you'll be able to tell exactly what it should do. And you can do that without actually implementing anything. We'll see examples of it, and I'll update the documentation so that it has some code examples too. All right, so for the scheduling, could be round robin or first come, first serve. In that, you just create a queue or a list, and it's a fairly simple algorithm. So run whatever the thread is at the front. If it yields, throw it to the back of the queue. In this lab, you have to do the context switch, and it will have to save all the registers and everything like that. But there is a handy dandy library that I will teach you to use in the next lecture that will do all the heavy lifting for you. So the threads you are implementing are going to be cooperative threads. So that means that they have to be nice and they have to yield in order for another thread to run. But if you want to extend your implementation to do preemptive threads, it's actually not that much, it's not that difficult. All you would do is get like a timer signal, and then whenever that timer interrupt comes into your process, you just call yield for that thread. So then you just constantly change it over and over again. So here is our next complication. Then we can ask questions and explore or do whatever. So let us explore this fun little program, because this is when things get real. So here we go. So we have a main. So once we start executing this, we'll create a single process with the main thread that starts executing main. So what it is going to do is create an array of pthread t's up to num threads, which in this case is 8. And then we will have a for loop that will create 8 threads and then set them all to execute this run function. And then after we create them all, we're going to join them all from the main thread. So they're all joinable. So I will let the main thread go ahead and wait for all 8 of them to finish. And then I'm going to print a counter. What is counter? I'm glad you asked. So counter is a global variable. So the only static here, if we forget what static means, it's just a global variable that I can only access in this .c file. Otherwise, static doesn't do anything. So all my run function does is each thread will loop 10,000 times and increment the counter by 1 for every iteration of the loop. So let's do some quick math here. If I have 8 threads and they each increment that counter 10,000 times, what should that counter be when I'm done executing? Yeah, 80,000, right? So each thread increments it 10,000 times. I have 8 threads. 8 times 10,000 is 80,000. So we would all agree that that's 80,000, should be 80,000? Cool. All right, so let's compile. 73,000. 73,373. Let's try it again. 62,000. Yikes. 76. Hey, there. Our program works, no bugs. Right? It's 80,000. That's what I expected. Now it works. I fixed it. I just had to run it a few times. So I run it a few more times, you know, I get 80,000 again, 68. So imagine if this program was calculating your grades or something like that. It's like, oops, sorry, you got a 62 instead of an 80. Oops. So anyone want to try and explain what is happening here? Yeah. Oh, that's a good guess. It's not waiting for everything to finish. So is it waiting for everything to finish? So it must be waiting for everything to finish, right? Because I'm waiting for, so unless I screwed up the loop bounds, which I didn't, so this executes the same amount of times as this. So for each thread I create, I join it. Yeah?
It's like race conditions. So if you have like the global variable is like one value, and two threads try to increment at the same time, it would like increment twice.
Yeah, they're sharing memory, right? So the only thing that is local to a thread is, well, essentially it's stack. So like this I is going to be unique to a thread. So each thread is actually going to execute 10,000 times. But this counter is a global. So it is shared between all threads. And this is why they have harped on you the difference between the heap and the stack, generally to prepare you for this. And the low-level pointer stuff was not an accident. It's because the details actually matter here. So we'll go over this more later, but just so you know, if I do plus plus count, and count is a global variable, well, this operation doesn't just happen in one step. So what your computer actually has to do is, well, each thread is going to read from the address of counter. Oh, I guess it's called counter. So it would do a memory read from that address. And it would read from that and then put it into a register. And then the next thing it would do to implement plus plus counter is it would increment that register, whatever it happened to be. And then the final step, if it's a global variable, well, it would have to write register value to whatever the address of the counter was. So there's actually 3 steps for that plus plus count. So I have to load the value from memory, put it in a register, increment the register, and then I have to go ahead and then write that new updated value back up to update that global variable. So what can happen, and don't worry if this is confusing right now, this is the heart of the hardest part of the course, so don't worry, we will go over it many a times. But what can happen even with 2 threads? Well, say I have 2 threads that are each trying to do this. So I could have the first thread read from counter. So I'll just make it slightly shorter into register. So in this case, let's assume that counter gets initialized to something like 0. So in this case, thread 1 will read 0 into some register value. So the register is now equal to 0. Then in the next step, it would increment that register. So now register is equal to 1. And then it would write to counter from that register. So now that counter global variable is now 1. And then ideally, the exact same thing happens. Oops. We could switch over to thread 2. And then thread 2 could read from counter. In this case, it would see the new value of counter. So instead of reading a 0, it would go ahead and read a 1. And then it would increment its register. So it would increment it to 2. And then it would write to counter. and then counter would be equal to 2, and life is good, right? 2 threads each increment once, so it should go from 0 to 2. So any questions about that? That's how it would normally work. Yeah.
So like, does it happen, so does this like switch between threads happen every time you increment? So like, if you increment it once, will it go to the second thread, and then after the second thread increments, it will go to the third thread, or is it just non-deterministic?
Yeah, so this is whenever it switches between threads. Did you have any say as to when the kernel will context switch between processes? No, so you have no say whether or not the kernel context switches between threads. So because of that, well, this is what would happen in the ideal case, but in the not, oh, yep.
What would happen if they start at the same time and they reach 0? Like if, what if thread 2 also reads 0 because it starts before thread 1 finishes?
Yeah, so in the not ideal case, oops. So in the not ideal case, well, thread 1 could start running, read counter into its register, and then we context switch to thread 2, in which case it would read from the same global variable, and in this case it is not updated. So it's going to do exactly what you said, and thread 2 is going to read 0, right? Now, at this point, we are screwed. So no matter what happens, if it switches back to thread 1, well, thread 1 with it, so the register is local to the thread, so it's already loaded as 0, so it won't change whenever we context switch back to it. We would increment it from 0 to 1, and then we would write out to that counter, and then counter would be updated to 1. Then if we context switch back over to thread 2, well, its register was 0, it's currently 0. It would do that increment, and if it does that increment, well, it would increment it from 0 to 1, and then it would also update the counter, and in this case, it would be updated again to 1. So I would see 1 when both threads actually update it. So instead of what I would expect, one thread writes 1, the other writes 2. If I get unlucky, well, then one may write 1 and the other may write 1 as well and just overwrite it. So this is like the crux of our problem, and it is called a data race, and you will learn how to fix these. And this is it. This is like the hardest thing. Data races are like the most notorious, hardest bugs ever to fix, and we'll explore why, as we go on, we'll need several lectures to actually cover it and how to defend against this. But does everyone understand that this is fairly bad? So it just turned out that sometimes I got really lucky, how I got 80,000, but, you know, oh, hey, luck again. But turns out I'm not always lucky. Oh, whoops. So it turns out, you know, 60,000, that's an unlucky one. 70,000, ooh, 50,000, yikes, real bad. 80,000, they're fixed. Yeah, so this is like the reason why programming is actually hard. All right, any questions about that stuff? Or are we fairly good? I didn't break you too bad yet.
Is there ever way to like implement it to weights? I don't know.
Yeah, well, if I wanted to, let's say, oh yeah, okay. Someone tell me how to fix this so it always prints 80,000, but we still create 8 threads. Anyone come up with a solution? Yeah.
Can I take a guess?
Sure.
Maybe before you block, you want to sleep, or you want to stop the thread before you block.
Like I want to sleep here?
Yeah. No, before you pthread join, you would want to sleep, maybe.
Here, let's try this.
It's
Th-
not equals 8,000.
This. All right, so if we learned anything so far, it should be that sleeping and it just working is not a solution. So it might work for some things, it might not work for others. So in this case, let's try it. Oh, this is going to be real slow. All right. All right, so this is already not satisfying. Okay, that got lucky. This is very not satisfying. Yeah. Either, go.
So like, I know for like you use like mutex, so you can like lock the global variable before you implement it.
Yeah, we don't know about mutexes yet. Yeah.
Make like a array sort of thing and then index each thread to like a true array.
Yeah, so I could create an array of these and then have each thread just update its own so that I essentially make some thread local storage for each one. And then I would probably have to add them all together at the end, right? To sum everything back up. So you actually just came up with MapReduce. So MapReduce, it's like a big data Google thing. You won't learn that until like 4th year. So that is one thing we could do, but I don't want to write that many lines. Another, yeah.
Just wait before the thread dies right after you create it.
So do this.
Yeah.
All right, let's see. 8,000. Seems pretty good. So this kind of fixes the issue, but what am I losing by doing this?
Isn't that just like running it in serial? It's not parallel now, right?
Yeah, so this is essentially just running it in serial. So I create a thread, it executes, I wait for it to finish. I create a new thread, wait for finish, create another thread, wait for it to finish. So at any given time, there is only one thread doing this, right? So if I have 8 cores on my machine, can I use all 8 cores in parallel? No. So if you want things to go vroom, vroom fast and you want things to run in parallel, well, we're going to have this issue. But this is a fix that will give you the correct outcome you want. But at this point, is this a smart idea? Probably not. It's probably going to be a lot faster just to have one thread that doesn't create anything else and just loops 80,000 times instead. That's probably going to be a lot faster. So you will encounter that whenever you try to like add threads to your applications. You might get into the situation where, oh, well, I'll fix all these problems by just essentially running it in serial. And then suddenly, in your desire to make your program go a lot faster, you have now just made it slower. You've made it still serial, but you've made it create threads and use threads on top of what it was already doing. So you can actually make things go slower by using threads. So any other questions? That's fun. All right, so we'll be doing threads for a while now. So we can go ahead and early or, yeah, we can end early, we can take a break, have a nice little breather, finish your lab 3 if you haven't done so already, and then be sure to come to the next lecture because we'll be doing like how you should start lab 4 and how you should use all the libraries you should be using. So just remember, pulling for you, we're all in this together, and this, again, hardest thing in the course.